In 1890, there were no electric motors in American factories. None. Not a single machine in a textile mill with 500 looms had its own motor. Not one lathe in a machine shop. Not one drill press. Not one saw. Not one piece of equipment had a switch you could flip to turn it on. So here's the question that should stop you in your tracks. How did any of this work? How did a steel plant shape tons of metal? How did a paper mill process thousands of sheets a day? How did factories operate at all? Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old machines' legacies alive. Imagine walking into a factory in 1890. Look around. You won't see what you expect. There are no motors mounted on machines, no electrical panels on the walls, no power switches within reach of the workers. The absence is disorienting. But then you look up. The ceiling is alive. Massive iron shafts span the length of the building, running parallel like the rafters themselves, except these are spinning. Always spinning. Leather belts crisscross the space above your head, some running straight, others at angles, all of them moving in a blur. The air catches the dust and makes the motion visible in shafts of light from the windows. The sound hits you next, a constant roar, part hum, part scream, as metal bearings hold spinning iron and leather whips through the air at 30 feet per second. Every machine below is moving, all at once, all the time. 100 workers stand at 100 different stations, and every lathe, every planer, every saw is already in motion before anyone touches a lever. The entire factory is one massive interconnected organism, and you're standing inside its mechanical circulatory system. Now think about the engineering problem. This factory has 300 machines. Each one needs power. Each one needs different speeds. A drill press spinning at 800 revolutions per minute, a heavy planer moving slowly with enormous force. Some machines need to start and stop independently throughout the day. A worker finishes one piece, needs to halt the machine, load the next piece, start again. But there's no electricity, no individual motors, just that one spinning shaft overhead, and somehow, impossibly, it powers everything. The solution existed, and it was purely mechanical. It required no technology that hadn't existed for a century. But the system was so complex, so foreign to how we think about power today, that even describing it feels like explaining an alien civilization. Engineers built entire factories around a principle that's now completely extinct. They solved the unsolvable using nothing but iron, leather, and physics. To understand how it worked, you need to start at the source of power itself, with the prime mover, and trace the path of energy as it spread through the building like branches of a tree. The system had a logic, a brutal elegance, and a cost that nobody in 1890 could avoid paying. At the heart of every factory stood the prime mover, and it was massive. Picture a coreless steam engine, towering 50 feet high in its own dedicated engine room. The flywheel alone measured 20 feet in diameter, a spinning disc of cast iron weighing 30 tons. The piston had a bore of 40 inches and a stroke of 10 feet. Imagine a metal cylinder the width of a barrel driving back and forth with enough force to generate 500 horsepower. The entire engine pulsed with a rhythm you could feel through the floor, a deep mechanical heartbeat that never stopped during operating hours. Some factories used water wheels if they sat beside rivers, wheels 30 feet across, turning with the patient, inexorable force of falling water. Later, stationary gas engines joined the ranks, but the principle remained the same. One engine, one source of power, and it was immovable. These prime movers cost a fortune. A large steam engine could run $20,000 in 1890 money, $500,000 in today's terms. You didn't buy two. You didn't have backups. You built your factory around this single beating heart, and when it ran, everything ran. When it stopped for maintenance or repair, the entire operation went silent. The engine fired up at dawn, built steam pressure for an hour, and then ran continuously until the evening shutdown. There was no switching it on and off casually. This was commitment. From the engine, power transferred to the main line shaft. A massive leather belt, sometimes 4 feet wide, wrapped around the flywheel and climbed to a pulley mounted on an iron shaft running the length of the factory ceiling. This main shaft was the spine of the entire system, made of wrought iron or steel. It measured 6 to 12 inches in diameter and could stretch 300 feet or more in larger facilities. The shaft sat mounted in heavy cast iron bearings bolted to the ceiling beams or brick walls, one bearing every 10 to 15 feet, to support the weight and handle the rotational stress. When the engine engaged, the main shaft began its rotation, 100 to 200 revolutions per minute depending on the factory's needs. Once it reached operating speed, it generated a deep, constant hum that became the baseline note beneath every other sound in the building. Stand beneath a spinning main shaft, and you feel the air move. The shaft itself weighs thousands of pounds, and that mass, rotating at speed, creates a presence. Workers learn to sense it, to maintain awareness of that ceiling-level rotation the same way you stay aware of traffic when crossing a street. The shaft ran hot from friction in the bearings. In winter, workers sometimes gathered beneath it for warmth. But now comes the question that makes the whole system remarkable. You have one shaft, spinning continuously overhead. Your machines are scattered across the factory floor 50 feet away, 80 feet away at different heights and angles. How do you get power from that single shaft to a lathe in the corner? The answer was secondary line shafts, and they turned the factory ceiling into a grid of spinning metal. From the main shaft, power transferred to smaller shafts running perpendicular or parallel throughout the building. These secondary shafts, sometimes called countershafts, measured 3 to 6 inches in diameter and connected to the main shaft through leather belts. A pulley on the main shaft, maybe 10 inches across, would drive a belt up or down to a larger pulley, say 20 inches, mounted on a secondary shaft 15 feet away. That difference in pulley size changed the speed. The secondary shaft would spin at half the speed of the main shaft, which is exactly what certain machines needed. Other secondary shafts used different pulley sizes to spin faster or slower, creating zones of different speeds throughout the factory. The belts themselves deserve attention. They were made of leather, stitched together in layers for the heavy-duty connections. Some were just 2 inches wide for light work. Others stretched to 24 inches for serious power transmission. The leather had to be thick enough to handle the tension, but flexible enough to wrap around pulleys without cracking. Workers joined the belt ends with metal laces, rivets, or special cement, creating an endless loop. These belts screamed through the air. A belt moving at 30 feet per second made a distinctive whistling sound as it whipped from one pulley to another. They crossed paths in the air, some climbing at steep angles, others running nearly horizontal. If you looked up in a large factory, you'd see 50 or more belts in motion simultaneously, a chaotic web of leather strips all pulling power from that central source. But the belts had problems. They slipped. Even under perfect tension, a leather belt loses 2 to 5% of its power just from slippage against the pulley. The leather stretched over time, requiring constant adjustment. Factories employed workers called belt men, whose entire job was climbing ladders to adjust tension, replace worn sections, and apply belt dressing, sticky compounds that improved grip between leather and metal. A belt under high tension carried enormous force. If the leather failed, if stitching gave way or a rivet pulled through, the belt could snap with the force of a whip, and anything in its path, tools, materials, people, took the hit. Large factories didn't stop at secondary shafts. Some had tertiary shafts, creating a 3-level distribution network. The main shaft fed secondary shafts, which fed even smaller shafts closer to individual work areas. Looking up from the factory floor, you'd see this canopy of rotating iron at different heights, all interconnected by crossing belts. Some shafts ran north-south, others east-west, creating intersection points where multiple belts converged on a single pulley. The whole system had to be balanced. Engineers calculated the load on each bearing, the tension in each belt, the speed ratios through multiple transfers. One miscalculation could cause a bearing to overheat and seize, bringing down an entire section of the factory. The visual was hypnotic. Shafts spinning at different speeds, belts crossing at angles, the constant motion overhead while workers moved below. New employees learned quickly to watch the ceiling, to track the spinning shafts and moving belts. to never walk directly under a high-tension connection. The danger was always present, hanging in the air above their heads, literally. Power now ran overhead throughout the factory in a network of spinning shafts, but the machines themselves sat on the floor 10 feet below. A lathe needed to turn, a drill press needed to spin. A planing machine needed to drive its cutting head back and forth. Each machine required its own connection from the nearest overhead shaft, and here's where the system became truly clever. More importantly, workers needed to turn individual machines on and off throughout the day without stopping the entire shaft network. That was the final puzzle, and solving it required one more layer of mechanical ingenuity. Each machine had its own small countershaft mounted directly on the machine frame or on a nearby post. This countershaft may be 2 inches in diameter and 3 feet long, connected to the overhead secondary shaft through a vertical or angled belt called a jack belt. The jack belt ran continuously just like everything else, transferring power down from the ceiling to this machine-level countershaft. Different pulley sizes controlled the speed. If the overhead shaft spun at 100 rotations per minute and you needed your lathe countershaft at 200, you used a pulley twice as large on the countershaft as the one on the overhead shaft. The countershaft itself spun constantly during operating hours, a small rotating axle right there within arm's reach of the worker, always ready, always live with mechanical energy. From this countershaft, the final connection drove the machine's actual working parts through gears or one last short belt. But here's the brilliant part, the detail that made individual control possible. The countershaft had 2 pulleys mounted side by side. One was fixed tight to the shaft. When it turned, the shaft turned. The other was loose, free to spin independently on the shaft like a wheel on an axle. The belt from the overhead shaft could be shifted sideways between these 2 pulleys using a lever or forked shifter within the worker's reach. When the belt sat on the loose pulley, it spun freely without engaging the countershaft. The belt moved, the pulley rotated, but the countershaft and the machine remained still. The machine was off. When the worker pulled the shifter lever, it pushed the belt sideways onto the tight pulley. Instantly, the countershaft engaged and began spinning, driving the machine to life through its gears or final belt connection. Push the lever back, the belt shifted to the loose pulley, and the machine coasted to a stop while the belt overhead kept running. This simple mechanism, 2 pulleys and a belt shifter, gave workers on-off control without touching the power source itself. More sophisticated machines used cone pulleys, a series of pulleys with different diameters stacked like a stepped cone. The worker could shift the belt between different levels of the cone while the machine ran, changing speeds on the fly. A lathe operator might run slow for a rough cut, then shift to a higher speed for finishing work, all by moving a lever that slid the belt from one part of the cone to another. Operating a machine this way required skill and timing. You didn't just flip a switch. You reached up, grasped the shifter fork, and moved it firmly to push the belt from loose to tight pulley. If you hesitated, the belt could catch wrong and slip off entirely. The engagement wasn't gentle. When that belt hit the tight pulley, the machine lurched into motion with immediate force. Workers developed a feel for it, a rhythm. They learned to anticipate the grab, to position their work before engaging power, to shift smoothly between speeds without thinking. Now here's what nobody tells you about this magnificent mechanical system. It was breathtakingly wasteful. A 500 horsepower steam engine burning coal around the clock might deliver only 100 to 150 horsepower of actual useful work at the cutting tools and machine surfaces. 70 to 80% of the power simply disappeared, converted to heat, friction, and wasted motion before it ever did productive work. The losses stacked up at every transfer point. The main shaft lost 10 to 15% just from friction in its bearings, all that weight spinning on metal surfaces that never stopped generating heat. Every belt connection bled another 5 to 10% through slippage. The leather couldn't grip the pulley with perfect efficiency, especially as it aged and stretched. From main shaft to secondary shaft, you lost power. From secondary shaft to counter shaft, more loss. By the time energy reached the actual drill bit or saw blade, only a fraction of what the engine generated remained available. The rest had transformed into heat radiating from bearings, sound waves filling the factory air, and vibration thrumming through the building structure. Think about what that meant economically. Factories burned mountains of coal to generate steam, and most of that energy never contributed to production. The fuel costs were staggering. The waste heat made factories unbearably hot in summer. Workers sweltered in buildings where hundreds of bearings radiated friction heat, while steam engines pumped even more thermal energy into the space. Yet factories accepted this enormous inefficiency because the alternative was worse. The alternative was no power at all. Inefficient mechanical power still beat human muscle power for any industrial-scale operation. You tolerated the losses because the system, wasteful as it was, still multiplied human capability beyond what any other method could achieve. But the inefficiency wasn't the only cost. The human price was brutal. Those spinning shafts and moving belts created a workplace of constant danger. Workers lost fingers, hands, and arms to the machinery with grim regularity. Hair caught in a moving belt meant scalping or worse. Loose clothing could snag on a pulley or shaft, pulling a person into the machinery before anyone could react. A woman's long skirt, a man's sleeve, a dangling tool belt, any of these could kill. The beltmen who climbed ladders to service the overhead systems faced particular risk. They worked at height among moving parts under high tension, and when accidents happened up there, they were usually fatal. The belts themselves were weapons waiting for a trigger. A 12-inch wide leather belt under full load carried tons of tension. If the leather failed, if a lacing pulled free, or a weak spot tore, the belt snapped with explosive force. The loose end would whip through the air faster than anyone could dodge, and a heavy belt moving at speed could decapitate. Factory records from the era are filled with these incidents. Brief mentions of workers struck by failed belts, crushed between pulleys, or pulled into shaft bearings. There was no Occupational Safety and Health Administration, no federal safety regulations, no requirement for guards around dangerous machinery. Insurance companies charged factories enormous premiums because the actuarial tables showed the truth. This system maimed and killed with predictable frequency. The noise alone caused permanent damage. A factory full of spinning shafts, screaming belts, clattering machines, and hissing steam created a sound environment that destroyed hearing. Workers went deaf gradually over years of exposure, losing first the high frequencies, then broader ranges, until conversations became impossible without shouting. Nobody wore hearing protection because the concept barely existed. The noise was simply accepted as the price of industrial work. Beyond safety, the system imposed rigid operational constraints. During operating hours, the shafts ran constantly. You couldn't shut down one section of the factory easily. If the main shaft stopped, everything stopped. Reconfiguring the factory floor to improve workflow or add new machines meant rerouting shafts and belts, an expensive and time-consuming process that required shutdown time and skilled millwrights. The layout of your factory was determined not by optimal process flow, but by where you could practically run shafts and belts. Machines clustered near shaft lines. Work areas shaped themselves around the mechanical distribution network rather than around the logic of production. Fire posed an existential threat. One blaze could destroy the entire shaft system, leaving a factory unable to operate even if the building structure survived. Maintenance required complete shutdowns because you couldn't safely work on a system while it was running. Starting up from a dead stop took time and coordination, getting all that mass spinning again, building up to operating speeds gradually to avoid shocking the system. The first electric motors appeared in factories during the 1890s, but they were expensive, unreliable, and viewed with suspicion by engineers who understood steam and leather belts. Early adoption was cautious. Some factories installed electric motors simply to drive their existing main shaft, replacing the steam engine, but keeping the entire distribution system of shafts and belts intact. The real revolution came later, in the first 2 decades of the 20th century, when small electric motors became cheap and reliable enough to mount directly on individual machines. Suddenly, each lathe could have its own 1-horsepower motor. Each drill press, each saw, each piece of equipment could operate independently with a simple electrical switch. No more overhead shafts, no more belt networks, no more counter shafts and shifter levers. Just a motor bolted to the machine and a switch on the wall. The transformation was staggering. Factories stripped out thousands of feet of line shafting. They removed the maze of belts overhead. The efficiency jumped from 20 or 30% to 80 or 90%. Power flowed only when and where it was needed. A worker could shut down their machine completely between jobs, saving energy. More importantly, machines could be placed anywhere on the factory floor. Process flow could finally dictate layout instead of mechanical constraints. Need to move a drill press closer to the lathes, unplug it, roll it over, plug it back in. What had once required days of shaft reconfiguration now took minutes, but the transition wasn't instant. It took 30 years or more for electric motors to fully replace line shaft systems. Factories had enormous capital invested in their existing mechanical systems. Those shafts and bearings represented years of investment, and they still worked. Many operations kept line shafts running into the 1940s and even the 1950s, particularly smaller shops that couldn't afford wholesale electrification. There was a generation of workers who learned both systems, who remembered when starting a machine meant shifting a belt, who watched their factories gradually convert to electric power one machine at a time. Today, the ghosts of line shaft systems remain visible if you know where to look. Old factory buildings still have mounting brackets on their walls and ceilings where shaft bearings once attached. You can see reinforced floors and ceiling beams designed to support thousands of pounds of rotating iron. The windows are placed in patterns that made sense when natural light had to reach beneath overhead belt networks. Some museums preserve working line shaft systems. Places like the Lowell National Historical Park in Massachusetts maintain operational textile mills where visitors can see and hear what factories once sounded like. The lesson cuts deeper than nostalgia. Engineers in 1890 faced a constraint that seemed absolute: no electric motors, and built a system that powered the Industrial Revolution despite losses and dangers that would horrify modern safety regulators. The system was simultaneously brilliant and brutal, innovative and lethal. Within a generation, electric motors made the entire elaborate mechanism obsolete. What had been impossible to imagine living without became impossible to imagine living with. Somewhere right now, we're operating under constraints we don't even recognize, building elaborate systems around limitations that the next generation will find quaint. The next time you flip a switch and a machine starts, remember the spinning shafts overhead that made that simple switch possible.